Okay, welcome to everybody. Today we have the last and the final lecture, the fourth lecture. This lecture has two parts. In the first part, we discussed the cosmology, which is obvious application of the general theory of relativity. And in the second part, we shall discuss exact solutions. Particularly, I will discuss two techniques. And then finally, in the last part of this lecture, I shall apply that particular technique to a particular problem. So, we start off our lecture. As you have seen, this is the plan of all the four lectures, and we have discussed the first three parts, and we are first two parts, and we are discussing today the last two parts, cosmology and exact solutions. These are the suggested books, as I have mentioned in the first lecture. So, let us start from the cosmology. Cosmology is in fact a Greek word, and it is a combination of two words. Cosmos means universe, and the logos means for the study of. So, in fact, this is the subject or scientific study of large scale structures of the universe as a whole. So, it aims to understand the universe origin, structure, evolution, and its ultimate fate. First, we define two important properties of the universe, that is the homogeneous universe and the isotropic universe. Homogeneous universe is the universe when all the properties of the universe are same at every point. So, it means universe is same, looks the same at all positions. So, when viewed on large scales, that is greater than the scale of galaxies, the universe appears uniform in composition and structure. In a homogeneous universe, the two important quantities, energy density and pressure, are uniform throughout the space. There are no preferred locations in space. The same physical laws apply everywhere. In isotropic universe, we have the same properties in every direction. I mean, when the universe looks same in all directions. This means when observed from any point in space, the universe exhibits no directional preference. So, isotropy implies that properties such as temperature, density, and pressure are same in all directions from any given point. So, the geometry of the universe does not favor any particular direction in the isotropic universe. So, these are two important properties of the universe. You can see from these diagrams. In the first diagram, we have the homogeneous universe, but it is not isotropic. In the second diagram, we can see the point in the center is isotropic. If observer is standing there, he can see throughout the space, it looks the same. So, it is isotropic, but not homogeneous. In the third diagram, we can see it is homogeneous as well as isotropic. Now, we come to the cosmological principle, which is in fact the combination of homogeneous and isotropy. So, according to this principle, the universe is homogeneous and isotropic. So, this means the universe looks the same to all observers at all times. So, this is very strong argument. Now, we can give two versions of this principle. The first version is called weak cosmological principle. According to this principle, the universe is homogeneous and isotropic on large scales in space, but not necessarily in time. So, it means with respect to time, it cannot be homogeneous and isotropic. However, in the strong cosmological principle, we have homogeneity as well as isotropy with respect to space as well as time. So, this is the strong version of the cosmological principle. As a matter of fact, the universe is far from being homogeneous and isotropic. However, we observe a lot of structures around us, we can expect that the universe can be well approximated as homogeneous and isotropic if we average over large volumes. The cosmological principle can be seen as sort of Copernican principle, according to which there are no preferred points or preferred directions in the universe. Our current model for the discussion of the universe is called the standard model of the cosmology and is based on the cosmological principle. Nevertheless, today there is a debate on the applicability of this model or this principle. Now we come to the Einstein universe model. The Einstein universe is a theoretical solution to the Einstein field equations. For the universe to look the same to all observers at all times, the physical parameters cannot depend on space and time. So, the universe must be static, homogeneous, isotropic, and spherically symmetric. So, in fact, we need to take the universe model like this. Here, obviously, nu and lambda are arbitrary functions of radial coordinate r. We can take the stress energy tensor for a static, homogeneous, isotropic fluid as follows. Here, it is the expression of perfect fluid. However, for the strong principle to be valid, rho and p, which are the density and pressure, must be constant here. Thus, the principle of energy conservation applied in the rest frame gives the following expressions. That is, the energy momentum covariant derivative of the energy momentum tensor must be 0. Now, I provide some details of the calculations, how to develop this model. In fact, if we calculate this energy momentum tensor, that is covariant derivative of the energy momentum tensor, we find this expression. I am not going into the detail. You can calculate the covariant derivative. This is very simple, and we have already done this thing, plus e raised to power minus lambda rho c square plus p is equal to 0. Now, you can see from this expression, this cannot be 0. However, either we have this thing 0 or we have this thing 0. So, we take nu prime is equal to 0. In the first case, you can see, and the second case, you have rho c square plus p is equal to 0. So, we solve both the cases and see whether solutions is viable or not. In the first case, when nu prime is initially, we calculate the non-zero components of the Ricci tensor. This has also been found in the case of Schwarzschild spacetime. I am just writing down because these will be useful to calculate the Einstein universe model. Plus 2 nu prime over r e raised to power nu minus lambda. This is the 0 component. This is r11 minus 1 by 2 nu double prime plus 1 by 2 nu prime minus lambda prime plus 2 lambda prime over r. r22 is 1 by 2 r nu prime minus lambda prime minus 1 e raised to power minus lambda plus 1, and finally r33, which is due to spherical symmetry, we can just write down r22 sine square theta. Now, for the since energy momentum tensor we have already written, so we can calculate its trace, which is given as AB TAB is equal to rho c square minus 3p. In the previous lecture, we have already written another form of the field equations, which is given as kappa rho c square plus p 0 0 a 0 b g 0 0 plus 1 by 2 rho c square plus p g a b. This is the expression of Ricci tensor when we take the trace of the Einstein field equations and then inserting the values of perfect fluid. Okay. Now we can calculate the Ricci tensor components using this expression as well. So, first of all, we take for the case first. That means nu prime is equal to 0. So, we insert this value in the R00 component and compare the two R00 from the last two expressions, and we can finally calculate that this is rho c square is equal to minus 3p. Okay. Now we compare R11 from the two expressions, and we have found this expression lambda prime over r is equal to minus 1 by 2 kappa p minus rho c square e raised to power lambda is equal to kappa p e raised to power lambda. And when we compare the R22 part, we have 1 by 2 r lambda prime minus 1 e raised to power minus lambda plus 1 is equal to kappa p r square e raised to power minus lambda. Now, if we solve these two equations, say 1 and 2, we see that we have the value of e raised to power minus lambda is equal to 1 plus kappa p r square by 2 over 1 plus kappa p r square. However, when we insert this solution into equation number 1, that doesn't satisfy. This means that this solution is not viable. So, not viable, or it is not a solution of these equations. So, we leave this solution. Now, we come to the second case. For the second case, that means we are taking rho c square. We have the second case rho c square plus p is equal to 0. Again, we proceed on the same lines. We in fact calculate, we can write now RAB is equal to minus kappa rho c square GAB. Now, you can see from the R00 and R11 expressions that we obtain nu minus lambda. This is very similar to the Schwarzschild solution. We have also done this thing there. Okay. When we use R22 from the Ricci tensor formula and the field equations, then we can find that e raised r into lambda prime minus 1 e raised to power minus lambda plus 1 is equal to minus r e raised to power minus lambda prime plus 1 is equal to kappa rho c square r square. Now, we integrate this expression. When we integrate, we can find e raised to power minus lambda is equal to 1 minus 1 by 3 kappa rho c square r square plus some integration constant, say we can put here a r. Now we can see from here that when we put r equal to 0 in this expression, this becomes undefined. So to avoid the singularity, we can take the integration constant to be 0. So in fact, we can find the solution, or we can write the solution 1 minus 8 pi g rho 3 cc square r square. We have also inserted the value of coupling constant. So this is the mathematical solution. However, when Einstein found this solution, he rejected this solution. The reason is that it is not physical. Since here we assume pressure negligible as compared to the density. So that means we need to take rho and p equal to 0, but that leads to the Minkowski space-time. So for this reason, he rejected this solution. So he in fact modified the field equations. So here is the point when the Einstein modified his field equations, and he said that strong cosmological principle is a not good principle to discuss the solutions. So in fact, he introduced this cosmological constant. Now we proceed on the same lines as we have discussed the two cases earlier with different Einstein field equations. So for the first case, we find the solution e raised to power lambda is equal to, say, a minus lambda r square. So this solution here is obviously arbitrary constant, and lambda is the cosmological constant. Using the conditions on the boundary, one can found a equal to 1. So in fact, and further we assume that for the sake of simplicity, that lambda is equal to r raised to a minus 2. But here please keep in mind, r is not the Ricci scalar, this is a constant. So when we assume these things, we can find the solution in the final form as given here. So here you can see this is the final form of the Einstein universe model, and here obviously r is a constant, not the Ricci scalar. So as you can see, r raised to a minus 2 is the cosmological constant. And in the second case, I mean for case 2, we can solve the system, and then we have the second solution. This is called D-star universe model, and similarly here r is not a Ricci scalar but a constant. Now we can have three possibilities of the cosmological constant. Number one, it is 0, and in case of 0, we have found the two solutions that were not viable. And number two, it should be positive, and in this case we have found the Einstein universe model as well as D-star universe model. Number three, it can also be a negative quantity. In that case, we have anti-Einstein universe and anti-D-star universe models. Okay, now we come to the Hubble's law. In 1929, Edwin Hubble found that almost all the galaxies are moving away from us. This occurs because the entire universe is getting larger, which indicates that the universe is in the expanding phase. So this is the famous law, mathematical expression of the Hubble's law, V equal to h naught into r. Here V is the recessional velocity, h naught is the Hubble constant, r is the distance, and Hubble found the value of Hubble constant as 500 kilometers per second, MP per second. However, later in 1958, Sandage found its value this is not correct. This is in fact I think somewhere 200. I mean, this is typos here because it is just repeating. However, the recent observations indicates that the value of H naught is 67.6 plus minus. So some says that it is about 70 plus. So anyway, this is a debate. Now we come to a short video.
From the tiniest particles to the largest galaxies to the very existence of space, time, and life. But how did it all begin? The origin of the universe is the origin of everything. Multiple scientific theories, plus creation myths from around the world, have tried to explain its mysterious genesis. However, the most widely accepted explanation is the Big Bang Theory. The Big Bang Theory states that the universe began as a hot and infinitely dense point. Only a few millimeters wide, it was similar to a supercharged black hole. About 13.7 billion years ago, this tiny singularity violently exploded. And it is from this explosion, this bang, that all matter, energy, space, and time were created. What happened next were two major stages of the universe's evolution. Called the radiation and matter eras, they're defined by key events that helped shape the universe. First came the radiation era, named for the dominance of radiation right after the Big Bang. This era is made of smaller stages, called epochs, that occurred within the universe's first tens of thousands of years. The earliest is the Planck epoch. No matter existed in the universe at this time, only energy and the ancestor to the four forces of nature, the superforce. At the end of this stage, however, a key event occurred in which gravity split away from the superforce. Next came the Grand Unification epoch, named for the three remaining unified forces of nature. This epoch ended when one of those forces, called strong or strong nuclear, broke away. Then, the inflationary epoch began, during which the universe rapidly expanded. Almost instantly, it grew from the size of an atom to the size of a grapefruit. The universe at this time was piping hot, and it churned with electrons, quarks, and other particles. Then came the electroweak epoch, when the last two forces, electromagnetic and weak, finally split off. During the next stage, the quark epoch, all of the universe's ingredients were present. However, the universe was still too hot and dense for subatomic particles to form. Then, in the hadron epoch, the universe cooled down enough for quarks to bind together and form protons and neutrons. In the lepton and nuclear epochs, the radiation era's last two stages, the protons and neutrons underwent a significant change. They fused and created nuclei. And in doing so, they created the first chemical element in the universe, helium. The universe's new ability to form elements, the building blocks of matter, cued the matter era. Much as the name suggests, the matter era is defined by the presence and predominance of matter in the universe. It features three epochs that span billions of years, the vast majority of the universe's lifespan, and includes the present day. The first was the atomic epoch. In this stage, the universe's temperature cooled down enough for electrons to attach to nuclei for the first time. Called recombination, this process helped create the universe's second element, hydrogen. This hydrogen, along with helium atoms, dotted the universe with atomic clouds. Within the clouds, small pockets of gas may have had enough gravity to cause atoms to collect. These clusters of atoms, formed during the galactic epoch, became the seedlings of galaxies. Nestled inside those galaxies, stars began to form. And in doing so, They cue the latest and current stage of the universe's development, the stellar epoch. The formation of stars then caused a tremendous ripple effect and helped shape the universe as we know it. Heat within the stars caused the conversion of helium and hydrogen into almost all the remaining elements in the universe. In turn, those elements became the building blocks for planets, moons, life, everything we see today. This ecosystem of everything was only possible because of the many stages in the universe's development. While countless questions about the origins of our universe remain, it's only a matter of time for some long-sought answers to emerge.
Okay. Now we start the very well-known universe model, and the mostly accepted model of the universe is the Friedman-Robertson-Walker universe model. Robertson, in fact, belongs to USA, Walker belongs to United Kingdom. This metric was found in 1935. They found independently, in fact, this metric. They were not aware of the earlier work of Friedman, who is the Russian scientist, and by combining these names, this is called Friedman-Robertson-Walker universe model. You can see from here, this is the universe FRW universe model. Here K is the scale parameter and K is the curvature, A is the scale parameter. If we take, it can be 0, +1, -1. When K equal to 0, we have flat universe model. When K is +1, it is closed universe model, and when we have K equal to -1, we have open universe model. You can have the diagrams of each of these three, and this is the flat version, and this is the closed universe model, and finally this is the open universe model. We can also show these three models by combining this picture. I mean, this model is the closed universe model, this one. This is closed, and this is flat universe model, and this is open universe model. So in some books, this figure is given. So I have taken this is from some book. Okay. In general, a flat space is not a flat space time. The flat universe is not a flat space time. In fact, flat universe will be flat when the Ricci-Riemann tensor is 0. So the space time is flat only when A is independent of time and K equal to 0. In such a case, we can redefine the radial coordinate to absorb the scale factor, and the line element of FRW becomes Minkowski space-time. One can calculate the Ricci scalar for this universe model. As you can see here, obviously this involves derivative of A, and you can see from here, when we take K equal to 0 and A as constant, this Ricci scalar vanishes. This is in fact the case of Minkowski space-time, but R may vanish even if the space-time is curved. As in general theory of relativity, you can see that the Ricci scalar equal to 0 if and only if TAB is equal to 0. This is the case of vacuum space-time. This we have already done in the case of Schwarzschild. We can also see from the last expression that R diverges if the scale factor is 0. Typical cosmological models start from a singularity, namely A equal to 0 at the initial time, that is the Big Bang. I would discuss briefly very soon. We can find the Krichmann scalar for this universe model as given here, number 3, which also diverges when A tends to 0. Here we note that the cosmological principle is quite a strong assumption only based on the requirement that the universe is homogeneous as well as isotropic with respect to space and time. It is completely independent of the Einstein field equations. If we impose the cosmological principle in a four-dimensional space-time, the geometry is described by the FRW universe model. If we specify that we are in GR and we know that matter content of the universe, we can find the scale factor as well as curvature. In some modified gravity, for a different matter content, we would find in general different solutions for the scale factor as well as k. Note that the cosmological principle cannot determine some global properties of the universe. Now, let us discuss the Friedmann equations. These are the equations which are in fact Einstein field equations from the Friedmann universe model. So, Friedmann equations are fundamental equations in cosmology describing the dynamics of the universe under the assumptions of general relativity and the cosmological principle. I am not going into the details of these equations, how these can be derived, but as we have discussed the Schwarzschild space-time and the Einstein universe model, these can be easily discussed anyway. These equations relate the expansion of the universe to its matter content, energy density and curvature. The first Friedmann equation is called energy equation, and this is given as follows. Here obviously A dot is the time derivative of the scale factor, G is the gravitational constant, rho is the density, k is the curvature and lambda is the cosmological constant. This in fact represents the acceleration energy equation. Next is the acceleration equation, second equation. Here you can see we have double derivative of the scale factor. Now we can have some observations from these equations. We can see from the first equation how the expansion rate is influenced by the energy density, curvature and cosmological constant. But in the second equation, which is the acceleration equation, here we have density and pressure. So, this equation describes acceleration of the universe expansion and how it is affected by the energy density, pressure and dark energy, which is in fact represented by cosmological constant. In the early universe, density dominates, while in the late universe, dark energy becomes significant. Some special cases, when the universe is flat, this equation, the first equation reduces to this form, and in the matter dominated universe, when pressure is 0, the second equation takes the following form. And in the third case, when we consider radiation dominated universe, P is equal to rho c square over 3, the second equation takes the form. These equations are very helpful to discuss Big Bang cosmology, cosmic acceleration and structure formation. Now we discuss some cosmic theories. There are different theories that have been used to resolve the issues of the cosmology. Number 1 is Big Bang theory, number 2 is the pulsating theory, number 3 is the steady state theory, and number 4 is the big bounce theory. I am very briefly discuss these theories. Number 1, Big Bang theory. As you know, this theory was developed by George Lemaitre in 1927. According to this model, the universe expanded from an extremely dense and hot state and continues to expand today. Then pulsating theory, you can see that this is a cosmological model that suggests the universe goes through an infinite series of expansions and contractions. The first diagram, left hand side, indicates the expansion, and the right side diagram indicates the contracting universe. And then steady state universe. This was discussed and found by Bondi, Gould, and Hoyle. They proposed this theory in 1948. This model suggests that the universe has no beginning and no end. And finally, the very recent, not very recent, but very interesting, and people are working on this model, bouncing cosmological model. This is an alternative to the standard Big Bang model. Because in Big Bang, you said, I mean, the universe starts from the beginning, from the singularity. So, to avoid this thing, this model didn't begin from a singularity, but instead has undergone a series of expansions and contraction in a cyclical process. This idea addresses some of the challenges left unresolved by the traditional Big Bang theory, such as problem of the initial singularity and certain fine-tuning issues. Now, I will discuss some cosmological parameters which are in fact very useful when we discuss these theories in cosmology. Number one, scale parameter or scale factor. As you have seen, A is the scale parameter which is used in FRW universe. So, this is a time dependent positive function which is used to parameterize the expansion of the universe and determine its size. This parameter is used to define cosmic expansion in different eras or in different directions. Next is the, its increasing behavior indicates the accelerated expansion, while its decreasing behavior indicates the decelerated expansion. Next is the Hubble parameter. This is specifically measure the rate of expansion, and its mathematical expression is given here. You can see it has two possibilities. Either it is positive or it is negative. It cannot be 0, because in that case the scale factor will become constant. So, when it is positive, we have expansion phase of the universe, while when it is negative, it means it has a contraction phase of the universe. Next is the deceleration parameter. This parameter represents the accelerating, decelerating, and constant behavior of cosmic evolution. This is expressed in terms of Hubble parameter or in terms of scale factor parameter as follows. Again, we can calculate and check whether it is positive or negative. If it is positive, then we say that the decelerated phase, while when it is negative, we have accelerated phase. Obviously, when Q is 0, we have no accelerated or decelerated phase, but it is constant. Next parameter is the equation of state parameter. This is in fact a relationship between matter variables like density and pressure, like this. Here omega is the equation of state parameter. It is used to differentiate the evolutionary phases of the universe. That is phantom phase when omega is -1, while when omega lies between -1 and -1/3, we have coanticis phase. And now again we have a short movie.
Story as told by science. In the beginning, there was an ocean of energy that drove a rapid expansion of space, known as inflation. There were ripples in the ocean. As inflation ended, the ocean of energy was converted into matter at the Big Bang. And the pattern of the ripples was imprinted into our universe as regions of slightly different density in the hydrogen and helium gas that formed shortly after the Big Bang. the denser regions of gas collapsed to form the first stars. And the first galaxies. And 9 billion years later, a new star formed in the Milky Way, the Sun. The star was joined by 8 planets, including Earth. And nearly 13.8 billion years after it all began, we emerged, blinking into the light.
We shall start with the symmetries. First of all, what is symmetry? In simple language, if we say symmetry is a property of a physical system which remain preserved under some change or shift. So, in geometry, a transformation is said to be a symmetry of an object if it leaves the object apparently unchanged. There are different types of symmetries: local and global symmetries, continuous and discrete symmetries, isometries or space-time symmetries. A global symmetry is one that holds at all points of space-time, whereas a local symmetry is one that has a different symmetry transformation at different points of space-time. Local symmetries play an important role in physics. And then continuous and discrete symmetries. A family of particular transformations may be continuous, like rotation of a circle. A discrete symmetry is a symmetry that describes non-continuous changes in a system. For example, a square has a discrete rotational symmetry. Continuous symmetries can be described by Lie group, while discrete symmetries are described by finite groups. Now, let us discuss isometries or space-time symmetries. In fact, this has already been discussed when we discussed the Killing equations and Killing vector. So, just for the sake of review, an isometry is a direction along which the metric tensor is retransported. So, its mathematical expression is given here: Lie derivative of some vector of metric tensor with respect to some vector. Killing vector fields can be further generalized to conformal Killing vector fields defined by the following expression. Here lambda is some constant. So, space-time symmetry is the most interesting class of continuous symmetries that involve transformations of space and time. These may further be classified as spatial symmetries that involve only spatial geometry associated with a physical system. Next is the temporal symmetries. This involves only changes in time. Also, we have spatio-temporal symmetries. This involves changes both in space and time. Minkowski space-time is the well-known example having maximum space-time symmetries with 10 Killing vectors. So, if you have more Killing vectors, it means you are going to end some easy space-time. Symmetries have a wide range of applications in various fields. For example, to find solution of differential equations or to reduce it to a more simpler form for integration, to find solution of boundary value problems, to classify special solutions, to deduce new solutions from known ones, to find conserved quantities using the most celebrated Noether theorem. So, this is most important, that you can find some conserved quantities through this process. Noether theorem is the well-known theorem which in fact involves the conserved quantities. This theorem states connections between symmetries of a physical system and their corresponding conserved quantities. It relates a class of conservation laws to symmetries of space, time, and internal variables. More precisely, Noether theorem states that if the lead derivative of a Lagrangian along a vector field y vanishes, then y is a symmetry for the Lagrangian and generates the conserved quantity. This is very important when we find the conserved quantities. Let us now discuss some basic formulation of Noether symmetries and Noether gauge symmetries. Let us consider the transformations depending upon the infinitesimal parameter rho. Here obviously rho is a small parameter, not the charge density or mass density. So, Qi is the function which depends upon this small quantity as well as generalized coordinate Qi or Qj. This can generate one parameter Lie group. The corresponding vector field with unknown alpha is defined as follows. Here alpha I depends upon the generalized coordinate. You can see the q dot, which is the generalized velocity. This is said to be an Noether symmetry generator for the Lagrangian, which depends upon time, generalized coordinate, and generalized velocity if it leaves the Lagrangian invariant, that is, Lie derivative of Lagrangian with respect to this vector is 0. Next is the Noether gauge symmetries. These are generalization of the Noether symmetries, as the presence of some extra symmetries is expected in this case. So, we consider again a vector field y such that y is equal to some function tau, which depends upon time and generalized coordinate, and xi, which depends upon the time and generalized coordinate. And here its first order prolongation is defined as follows. Here obviously tau and xi are unknown functions that needs to be determined, and t is the affine parameter instead of some other thing. So, this vector field is said to be Noether gauge symmetry for the Lagrangian if there exists a function like g which depends upon t and generalized coordinate such that it satisfies this equation number 2. Here d is the operator which is defined here. This is a total operator. So, the corresponding conserved quantity is defined by this expression. Now, we define cyclic variable. This is very important variable because it facilitates the calculations. Variables that do not appear in the Lagrangian explicitly are called cyclic variables or ignorable coordinates. For example, if we consider the Lagrangian of a body moving in a 3-dimensional space in spherical polar coordinates, we can write the Lagrangian in the following form. Here obviously the first part is the kinetic energy, while the second part is the potential energy. You can see that in this system we have r, theta, phi 3 coordinates, but we cannot see phi in this Lagrangian. That means phi is the cyclic coordinate. These are very useful to reduce the Lagrangian into a simpler form and hence the field equations. Okay, before going to the second method, that is the decoupling technique, I would discuss modified gravitational theories. First, I defined that if we consider baryonic matter plus dark matter, we should have total energy of the universe, but we don't obtain this total energy. This means there is something which is missing, and this missing energy is called dark energy. There are many observations or evidences which indicate the existence of this mysterious part, like supernova, WMAP, SDSS, galactic cluster emission of X-rays, large scale structures, weak lensing, etc. These indicate the existence of dark energy. Now, it is well known that the composition of the universe has the following structure. It contains about 68.7% dark energy, 26.4% dark matter, and 4.9% ordinary matter. This means dark energy has the huge budget of energy in this universe. However, we don't have much information about this object. Now, there are some proposals to discuss dark energy. Number one, we can discuss dark energy through modified matter models like cosmology constant. Cosmology constant is the strong candidate to discuss dark energy. Quintessence, K-essence, Chaplygin gas, and tachyon fields. So, these all in fact come from the modified matter models. This is one way to discuss dark energy. And the second part leads to the modified gravity models. These indicate alternative theories of gravity like Gauss-Bonnet theory, Horava-Lifshitz gravity, FR theory of gravity, FT theory of gravity, FRT theory of gravity, higher dimensional theories, scalar tensor theories, and many more. But I have mentioned some of these alternative theories of gravity. But all these theories try to discuss mysteries of the dark energy. Now, let us discuss some motivations why we should consider modified gravity. In the standard lambda CDM model, lambda cold dark matter model, the gravitational interaction is described by general theory of relativity. The main reason is related to its remarkable agreement with a wealth of precession tests of gravity done in the solar system. These tests include the well-known test, the classical test of gravitational redshift, the lensing of the light from background stars by the sun, and the perihelion shift of Mercury, and many other tests. So, general theory of relativity is also in good agreement with the tests that involve change in the orbital period of binary pulsars. Despite of these tremendous successes, one can still think of a few reasons to suspect wishes that GR doesn't provide us with the full picture. Now, the question is whether general theory of relativity correct on large scales. Well, the above tests probe the gravitational law only on scales smaller than the solar system. In other words, there is a room for deviations from GR on cosmological scales. Well, modified gravity can be a dark energy. Dark energy is the general name given to any form of energy with negative enough pressure to have repulsive gravity. So, its existence is postulated to explain the observed accelerated expansion of the universe. The argument for modified gravity is that dark energy may follow from our wrong use of general theory of relativity on large scales. In other words, what we think are the effects of dark energy may simply be the effects of corrections to general theory of relativity that we are still unaware of. Next, whether GR has no quantum limit. A final way to go ahead and modify GR is to remind that this theory doesn't have a well-defined quantum field limit. So, taking for granted that all interactions must have a quantum field description, GR cannot be the final answer and must be corrected. Well, F for gravity is the popular among modified theories due to its applications in cosmology and gravity, such as inflation, dark energy, local gravity constraints, hierarchy problem, and unification of Gert's grand unification theories with gravity, cosmological perturbations, and many others. FR theory is in fact the simplest generalization of general theory of relativity. This theory is used to find spherical symmetric solutions in weak and strong gravitational backgrounds, bringing suitable cosmological models where accelerated expansion can be achieved by taking any negative power of the curvature like 1 over r term. Higher order terms always give an even number of the field equations. For example, if we have r square gravity, then we have fourth order field equations. If we have r box r, we have sixth order field equations. And if we have r box square r, we have eighth order field equations, and so on. We can extend this idea. Using conformal transformation, the term with second order derivatives corresponds to a scalar field. For example, fourth order gravity corresponds to general relativity with one scalar field. Sixth order gravity corresponds to GR with two scalar fields, and so on. So, FR gravity is equivalent to scalar tensor theory as well as to general relativity with an ideal fluid. The FR gravity is a simple generalization of GR in which we replace the Ricci scalar in the Einstein-Hilbert action. So, the action for the FR theory is given here. You can see from this action that we have in fact replaced R Ricci scalar with an arbitrary function FR. Obviously, the corresponding field equations will be as follows. Here you can see F in subscript R indicates partial derivative of F with respect to capital R. Here T alpha beta M indicates matter part of the energy momentum tensor. Well, you can see the notations FR and box, and here is the covariant derivative notation. Well, it is easy to find trace of the field equations. Now we can discuss the viability condition for this model. This indicates that the first and second order derivatives of F must be positive. Okay, in order to apply these solutions in FR theory or some other theory, we need isotropic fluid, which is given here. This is also called perfect fluid. We have discussed already this solution, this perfect fluid, today's lecture and also in the previous lecture. Here we have taken gravitational units, so we have taken C is equal to 1. And an isotropic fluid, you can see here, an isotropic fluid means the pressure is direction dependent. So, we have radial pressure as well as tangential pressure. So, we can find analytical or numerical solution of the field equations to describe physical characteristics of stellar configuration. In general relativity, a model of an isolated star generally consists of a fluid filled region and an exterior region which must be matched smoothly with an interior one. So, this is done by using the junction conditions. So, formulation of exact interior solutions is a complicated problem due to nonlinear nature of the field equation, except in the simplest cases, and which is the perfect fluid distribution. Now, I would describe the gravitational decoupling approach. This is a very recent approach that has been used by many people to find the solution of the Einstein field equations. So, the gravitational decoupling through minimal geometric deformation method has shown significant results in obtaining physically acceptable solutions corresponding to spherical relativistic configuration. This is not only a new concept, but also provides a large number of attractive ingredients in the quest of new spherical solutions. This has become a subject of great interest in cosmology as well as astrophysics. In this technique, the perfect fluid is coupled to other forms of matter, which is theta a alpha beta here, through coupling constant to describe more realistic scenarios. In general relativity, it is described as follows. Well, we have the field equations G alpha beta hat is equal to kappa T alpha beta hat, and we add some source, some other source theta alpha beta, and this xi is the decoupling parameter. And this technique was initially developed by Orville, and later many people has done. So, what is the procedure? In fact, we solve the Einstein field equations to find the geometric function. Then we solve the second equation, which involves the new matter part, to find the solution of G alpha beta steric and theta alpha beta steric. We combine these two solutions to find the original solution, which is the solution of the field equations. Well, this is the diagrammatic picture of the procedure. Initially, we add a new gravitational source in the isotropic energy momentum tensor. Then we pick a known isotropic solution and apply geometric deformation on the metric coefficients. We split the resulting field equations into two sets. The first set corresponds to the isotropic part or isotropic fluid. The second set is associated with geometric deformation, and this new source is equivalent to quasi-Einstein field equations. Now, in the next step, we find the solution of the quasi-Einstein field equations, and finally, we combine the solution of both sets to find a final solution. Let us discuss some physical characteristics which are used to check the solution. Number one, the maximality condition. A stellar object requires that the behavior of energy density and radial pressure should be positive, finite, and maximum in the interior. Maximality condition is used to show the maximum behavior of energy density and pressure at the center of stars. So, this is the condition to find the maximal behavior. This is the usual way to find maximum or minimum. Next is the energy bound. This is very important to check the viability of the solution. In order to describe some physically realistic matter distribution, some restrictions must be imposed on matter that are known as energy conditions. These conditions play a vital role in understanding the nature of matter. If these conditions are satisfied, then we say the matter is ordinary matter. If these conditions are not satisfied, that means we have exotic matter. Now, these conditions can be described as follows. Number one, the null energy condition. Number two, the strong energy condition. Number three is the dominant energy condition, and number four is the weak energy condition. You can see these conditions are described in terms of energy momentum tensor. U is the velocity, K is the null vector. Okay. You can see from this figure that the relationship of these energy conditions is the following. So, this indicates all conditions imply to null energy conditions. So, if the null energy condition is very important. So, if we can check the null energy condition, That means we can conclude our result. Next is the stability, because this is also very important concept in stellar system. The ability of an object to return to its original form against applied forces is called the stability. The existence of gravitational object is ensured by analyzing its stability against perturbation. Stability can be checked through different techniques. We are mentioning here some of these. Number one is the speed of sound. This depends on the properties of the substance through which the wave is traveling. So, for a stable structure of a compact star, the speed of sound should be less than the speed of light. That means this speed of sound must lie between 0 and 1. And the speed of sound is defined to the partial derivative of pressure with respect to density. Next is the adiabatic index. The stiffness of equation of state for a given energy density is described by the adiabatic index, and this is denoted by this symbol. This has fundamental role to examine the stability of stellar structure. For the sake of stable structure, it must be greater than 4/3 in the interior of the stellar object. Its expression is given by as follows. Here obviously rho and P are the energy density and pressure. Next we discuss junction conditions, because these are very important. Junction conditions, in fact, for the sake of finding solution of the field equations, we need these conditions. So, to describe every region of space time, the interior and exterior solutions must provide a single solution in some coordinate system. As you know that if we consider, for example, sphere, we have its interior part as well as exterior part. So, these two parts must be matched at some boundary. It is much easier to find such solution by joining the interior and exterior solutions together. So, some conditions must be put on them. These are called matching conditions. These conditions allow the smooth matching of the interior and exterior regions of space-time. The conditions for smooth matching of exterior and interior space-times are given as follows. Number one, the continuity of line elements over the hypersurface. This is the first condition. And the second condition is the continuity of extrinsic curvature over the hypersurface. This is given as follows. This is in fact is the Darmous matching condition, and if there is discontinuity, then we have, if there is a discontinuity in the extrinsic curvature, then we have Israel junction condition. Now, I would like to apply this procedure to some system in FR theory. Well, this is our paper which has been published in European Physical Journal C. I will discuss this paper here so that we can see the application. Let us consider the spherically symmetric space-time. Here obviously mu and lambda are radial dependent functions. So, we need to consider the matter distribution, and here we take as follows. This is the total energy momentum tensor. The first term is the matter part, usual matter part, and second term we are adding in fact some additional source, and in the third part we are taking some more additional part, and we can see that this is equal to T tilde plus chi theta. In fact, we have combined the first and third terms to denote with tilde. Here obviously chi is the decoupling parameter, and you can see the F term. F term is due to the FR theory, and obviously if we can have this term 0, then we go back to the general relativity. Now, we can write down the Einstein field equations. Well, in the case of FR theory, these are given as follows. And you can see that we are considering the energy momentum tensor, and that means the system must be conserved. So, conservation equation can be written as, obviously I am not going into the calculations, but one can calculate all these things. Because this system is complicated, we must need to apply some FR model to solve the system. So, Stravinsky model is very important, which has been used for inflation theory. So, we use this model here, and the field equation take the following form. Here we, as you can see, we have functions f1, f2, f3, and these are given here. These functions contain the modified terms. Obviously, prime means derivative with respect to radial coordinate. Okay. Now, we can identify the effective energy density and pressure components. Effective means that we are adding something in the usual matter part. So, rho tilde means we have added the density of the usual matter and density due to the terms of FR theory, and their chi theta is the in fact due to the decoupling or some other new source. Similarly, we can write the radial and tangential pressure components. The anisotropy in the interior of celestial objects takes the following form. Obviously, this comes due to the anisotropy. If there is no anisotropy, then this will be 0, and in this case tangential and radial pressure will be equal. Now, we apply the decoupling technique. In fact, decoupling technique, there are two types of decoupling technique. One is the minimal decoupling technique, and the other is the extended geometric decoupling technique. In the minimal technique, we just modified one component of the metric function, while in the extended we modified both metric functions. Here we are using extended geometric decoupling. So, that means extended geometric deformation technique, that means we are changing both metric potentials. So, here HR and GR are the new functions we are adding. So, using these functions, metric functions, we can write the field equations, and then we can separate these equations. First set corresponds to chi equal to 0, that is the isotropic case, and this describes the isotropic configuration as follows. So, these are the matter variables in the isotropic case that obeys the following continuity equation. The second set of equations comprising some additional source that leads to the following form. Obviously, this is complicated because new source or new ingredients are coming in these equations. The corresponding equation of continuity is the following, and theta 0 0, theta 1 1, theta 2 2 are components of the new source. So, using deformed metric components, the continuity equation takes the following form. The exchange of energy between the two sources is represented as follows. To solve these equations, we need some type of solution, and here we are using a well-known Karori-Barwa solution. This is a well-known isotropic solution. This is well-known for the reason that it is singularity-free solution. This was initially used for charged objects. However, later this solution has also been used in the absence of charge in general theory relativity as well as in other modified theories. So, isotropic solutions, in fact, we consider a well-known KB or Karori-Barwa model for perfect matter distribution in the background of spherically symmetric spacetime. This is given as follows. This is the Karori-Barwa solution. Here, obviously, beta, so B and C, A, B, C are constants that will be found through junction conditions. The corresponding energy density and pressure take the following form. Because it is isotropic, so we have rho and p as. We can calculate the constants by the smooth matching with Schwarzschild exterior spacetime, and these constants have the following values. Now, in order to solve the set of quasi field equations, we need additional constraint to close the system. So, for this purpose, we implement a barotropic equation of state on theta. This is given as follows. Here we take delta equal to 1 and gamma equal to 0. Next is the mimic constraints. We also imply two additional constraints, that is density like constraint and pressure like constraint. So, in this case, obviously we obtain two solutions, and then we discuss the viability and stability of these solutions. Solution 1, we adopt density like constraint such as, so corresponding equation of state and mimic constraint yield the following decoupling functions. The continuity of the first fundamental form yields the following expressions. So, now we can finally calculate the effective matter variables. You can see these expressions are much complicated, but and does not provide any insight unless we take their graphical view. So, this is the complete solution, and expression for an isotropic factor is the following. Now, we can discuss the graphical behavior. Obviously, we shall discuss the graphical behavior for some particular values. Here we take decoupling parameter as 0.05, 0.06, 0.07. I am considering three different values, and we also consider a particular star x1 which has mass and radius as follows. So, this is the these are the plots of effective density, radial pressure, and radial tangential pressure, then anisotropy. You can see from the first graph that density is a positive role. I mean, it has maximum value, then it is decreasing, but remains in the positive range. This is the required for the physical viability. And secondly, we also see pressure, tangential and radial pressure both remain in the positive range. They are maximum at the center and then decreasing. Similarly, we can see the anisotropy behavior which is expanding. So, these all variables or these all ingredients lie in the physical range. Next, we see the energy conditions, and you can see the plots of rho effective and PR effective for solution 1, and again we can see these show the positive behavior which is the required behavior. And next you can see the behavior of sound speed, and this is again we can see in the radial and tangential pressure, and you can see that the value of radial and tangential pressure lie between 0 and 1. So, this indicates the stable behavior of our solution. Here you can see another method to check the stability, and this means that this gamma must be greater than 4/3, and you can see from the graph for 3 different decoupling parameter that satisfies this condition. Similarly, we can extend for the second solution. We obtain the second solution by applying constraint on radial component of theta as given here. Consequently, when we apply this constraint, we have the following deformation functions. Here rho is given as follows. These are the matching condition, again the same in fact situation. So, the finally the effective density, effective radial pressure, effective pressure and anisotropic factor are given by as follows. These are in fact for the second constraint, and you can see that again these are very complicated. We cannot have any insights unless we have graphical analysis. Here in fact we are taking sigma is equal to 0.01 and plot graph for different values of decoupling parameter, that is 0.1, 0.2, 0.3. By taking again the same star. So, in the first graph you can see that you have density, pressure, radial and tangential pressure as well as anisotropic factor. You can see all the factors are in the required range. Density is positive, pressure has maximum values at the center, that is radial and tangential, and anisotropy has the increasing behavior which indicates the expanding behavior of the universe. And similarly we can check the energy density behavior, and you can see this is positive. So, it satisfies, that means this solution is viable. And finally, we can check the stability again through two methods. Number one, we are taking the speed of sound, and you can see the speed of sound lies between 0 and 1. Both radial as well as tangential pressure, and the adiabatic index you can see here, this is also in the range, that is it is greater than 4/3. So, this indicates that it is stable. So, in fact we have applied the decoupling technique to extended geometric deformation, and we have found two solutions, and both solutions are checked through viability conditions, through energy conditions, through stability, and both are in the required range. So, these both solutions are physically viable as well as stable. We can also check some other quantities, even we can apply this technique to find black hole solutions, some cosmological models, etc. So, this technique is very important to find interesting stellar objects and to find the exact solutions. Obviously, this is one of the hot topics to find exact solution. When we find exact solution, we can discuss many other things. So, with this solution, I would like to finish my lecture here, and before closing this session, I would like to invite you to have your comments, your feedback, your questions, etc. So, open to the audience. Well, if there is no question, then we would like to close the session. But before closing, I would definitely like to thank many people. First of all, I would like to thank SIMPA, International Center for Applied and Pure Mathematics, and Ms. Hela is very cooperative lady who arranged all these lectures in a very efficient way. Thank you, Ms. Hila. I don't know I have pronounced your name rightly or wrongly, but I try to. Next is Dr. Sarfraz, who's in fact in ComSat's Lahore campus, who in fact coordinated all these things in Pakistan. How I mean, he took the responsibility with SIMPA and VU Virtual University, and though he is in Germany, but he facilitated all these things. Thank you, Dr. Sarfraz. And obviously, a very big team in Virtual University, Dr. Babar Ali, who's the main guy, and then Mr. Azhar. And there are many people, I cannot take their name, but I'm thankful to all these people. I mean, cameraman, some makeup artist, and some other. This is obviously, you know, a big team which is doing very good work here. So I would like to thank the rector of this university as well. So thank you, Virtual University. And finally, I would like to thank my student as well as my colleague at University of Lahore, Dr. Muhammad Zishan Gul, who in fact remained involved in different things and providing facility in different ways. Thank you, Dr. Zishan, and thank you all. This is a good opportunity to talk to you, and this is obviously a very strange and good experience for me to come through online camera first time, and I hope people have enjoyed the lectures, and you can send even feedback through email or some other way to me. Thank you very much, and Allah Hafiz.